obviously with this shifting, you are able to do this many times. But the thing that really matters is this next 10 values. This next 10 values. I mean, we want to see the error, how much error this last 10, the future 10, or I should say like the 51st to the 60th elements. I mean, that you predicted, like how far away they are from the ground truth. This is what we really care, right? The previous, value, yeah, we will use that for training, but we are not going to use that for evaluation. But during evaluation, what matters is the accuracy of the 51st to 60th, okay, elements. So yeah, I mean you should define a separate MSE that care only for the last time step. Okay. So we define this. Okay, this return Keras matrix, mean square error. Okay, the last one. Okay, and then once you define this last time step MSE, I mean you can have your optimizer. Okay, we use Adam here, and then we compile our model, which use the loss function MSE optimizer. Okay, metric optimizer is the Adam. Okay, the matrix is last time step MSE. Okay, so these two are different. This one is to measure the performance of the model. This one is used during training. Okay, you need to be very careful to understand the difference between these two. Okay, so if you use this and train this model, the MSE you get is about 0.006. Okay, the previous one gives you the MSE of like 0.008. So this one is 25% better than the previous model. The previous model is the sequence to vector. This one sequence to sequence. I mean, give you even lower MSE. So this is a better approach. Okay, 25% improvement is not is significant. Okay, so obviously you can combine this approach with the first one. What do I mean? Okay, for example, say you want to predict like a long-term time series. Say like okay, use the first 50 time steps to predict next 50 time steps. Then what you do is that okay, you use this one to predict the next 10 value, and then use this sequence to predict the next 10 time value and so on. So you can apply this thing 5 times to predict like the next 50 values. So sort of like combining the first approach and the second approach. So obviously, I mean, when you do that too much, okay, you still get like error accumulation, right? So when you should weigh weighing how many additional sequence you want to predict. I mean, each time. Okay. So for example, okay, if you use like the first 50 to predict the next 10, okay, that's reasonable, right? That's reasonable, okay, because you should have enough information to predict the next 10. But let me use a very, extreme example. Okay, say you have the first 50 value, and you want to predict like the sequence of the next 100 sequence. Then, okay, you can use the first 50 to predict next 10, and do it 10 times, right? Okay, so that's what we meant by combining these two approaches. okay? Then, I mean, because each time you get the 10 additional value, and then you do it 10 times, you get the next 100 values, okay? But if you say, oh, I don't like error accumulation, let's do it in one prediction. So you use the first 50 to predict next 100 in one try. Probably that's not going to perform very well. Why? Think about that. You don't have a lot of information to predict this long, right? In one prediction. Okay? So this is like a, trade-off here, okay? I mean, obviously, if you have a long sequence and you predict like a, shorter sequence, it will give you a much accurate prediction, and then you can tap on that more accurate model. I mean, several times, okay, to form a longer prediction. Yes, but on the other hand, okay, if you use a shorter sequence and you expect to predict like one long sequence in just using, just you want to train a model to do that. That model, most likely will not perform very well. Okay, it's just because you don't have enough information. Okay, so this is like which these two approaches, yeah, they can be combined. As for like how do you combine them? That's something you can think about. Actually, for the project 3, okay, you are required to predict like the next 6 hours, PM 2.5, right? So say, if you just use the previous 3 hours to predict next 6 hours, well, most likely it's not going to perform very well. Okay, just want to give you an idea. You probably want to use a much longer sequence to do the prediction in order to make it like the next 6 hours prediction better. Okay? So also, okay, when you forecast a series, okay, it is useful to have some error estimation, okay, for your prediction, okay, like how accurate or how bad your prediction is, okay. So for this purpose, okay, the MC dropout is a good technique to apply. Okay, we talk about MC dropout in chapter 11. Okay, 2 chapters ago. Okay, so basically you can add MC dropout layer. Okay, with each memory cell, and this will help you, to estimate what we call error bar, or like the variance, okay, of your prediction. So which will you get a mean and a standard deviation, okay, which will help you to determine, okay, if your prediction is trustworthy or not. Okay, this is important. For many time series forecasts. For example, like if you want to predict like the stock market trend, okay, because you are investing money on it, right? So obviously you want to make sure, okay, your prediction is accurate enough, okay, so that your money you invested is not going to be a waste, okay. So, okay, at this point, okay, we finished like a lot of discussion as I mentioned at the beginning of this chapter, okay, there are, the island has some issues that we need to deal with, okay. Yeah. So, for example, when it comes to predicting the forecasting time series or handling other kind of sequence, RNA, is used for that purpose. But they do not perform well on long time series or sequence. Why? Okay, so the first, to train on long sequence, okay, we must run it over many time steps, making the unrolled RN through time a very deep network. Here, when we say deep network, I'm talking about here. Okay, we need to, unroll many steps. Okay, so when I say it's going to be a deep network, I'm not talking about the depth here. I'm talking about the depth horizontally. Okay, because you are going to expand your island through many time steps. Okay, which will create some issue. Okay, because the depth is not as there are two depths that we are discussing here. The one of depth is the number of layers, which is the same as like as we discussed for the other networks such as CNN or MLP. But the other depths, this unrolled through time. Okay, this is especially, the case for long sequence. Okay, and this type of thing, okay, only is this issue only happens in RNN. Okay, you don't have that in CNN, you don't have that in MLP. Okay, so I just want you to be aware. Okay, why training a long sequence? Okay, you encounter issue. We need to explain, we need to discuss, here, different. Where is it? Okay. Okay. So this okay. When it gets deeper, okay, even though we are talking about the other dimension, deep other dimension. Okay, yeah, the network, okay, the training of the network may suffer from unstable gradient problem. Okay, so it may take forever to train, or training may be unstable. Okay, another issue, okay, when RNN processes a long sequence, it will gradually forget, what we did at an earlier sequence. Okay, so the first input in the sequence, it will gradually be lost. Okay, especially during the unroll through time process. So what do we do? Okay, so let's talk about these two problems. Okay, two issues. How do we solve that? Okay, the first issue. Okay, unstable gradient problem. Okay, we talk about many ways to deal with that. Especially in chapter 11. Okay, so for example, good parameter initialization. Remember the He initialization or Glorot initialization. All those parameter initialization or faster optimizers. We talk about Adam, we talk about Nathan, all those optimizers, or dropout. Okay, this actually still helps. They are still useful. They are still useful. Okay. However, okay, one thing is slightly different. Non-saturating activation functions such as reloop, okay, may not help as much here. Okay. Why is that? Okay. They may actually lead the RNN to be even more unstable during training. Okay, because when you're doing gradient descent update, okay, the weights in the way that increase the output slightly at the first time step. Okay, well, here. When you're doing the gradient update, okay, keep in mind, okay, I mean this training, okay, for one iteration, okay, this expansion, or like unrolled through time, it's just one iteration, right? So this gradient flow back. Okay, even though I show you, okay, they look like okay, you have this and this and this and this. They are different model, right? They looks like a different model, but they actually all this represent the same thing, right? All this represent the same thing. So when you are calculating the gradient, yeah, you are calculating the gradient for this, but actually this and this, they actually share the same weight because they actually are the same thing, right? Even though we are unrolled through time, but they represent the same stuff here. So they use the same weight. All these weights are the same, and this during one iteration. So if your activation function result in slightly larger result, then those larger result, because you are using the exact same weight, that slightly, increased result is going to be enlarged and enlarged to a point that it explodes. Okay? So because this unrolled through time is special in our, as I said, I mean, this is